All right, everyone, yet again for another lecture on regression. These next few lectures are going to be quite intense. All right, so I'd like you to really pay attention and try to review the videos when you are at home, so that you are up to date with everything we're talking about. We're going to try to cruise quickly, but just slow enough to try to understand everything. But first, to remind you and to check your memory on where we left off last time, I want you to take a moment and consider the following questions. What is the simplest description of a set of data? So you're given a set of data. What is the simplest metric that you can think of to describe those data? Next, describe the standard deviation. I want intuitive terms. I don't want math. I want you to be able to explain it to someone on the bus, okay, who doesn't know statistics. And describe the standard error in the context of regression, all right? So note these questions. I will see you on Zoom. All right, I am here on Zoom with you. Looks like that worked out. I saw Sami giving me thumbs up. All right, do we have any takers, or should we do the Wheel of Misfortunes? Abby. Every time I bring up that wheel of names, I remember what you called it. That's funny. All right, so let's start with the first question. Let's spin the wheel. All right, so Ellie, do we have Ellie with us today? Cannot see all of you.
Yes, I'm here.
All right, Ellie, do you want to take on the first question?
Sure. So a simplest description of a set of data. Probably just the average or the mean is what I would say.
Yep.
Yeah.
Spot on. Yes. All right. So let's do the next question. Describe the standard deviation. Let's see. Martha, are you with us?
Hi.
Hi.
Yeah, I'm just reading the question. Just to let you know, I don't know if anyone else is experiencing this. There's another big lag between YouTube and the lecture. I could be the only one. The standard deviation is like if you were to average how far your data point is from like a linear fit, I think.
The standard deviation? No. So,
Okay.
so do.
Whoops.
All right. So hold on. I'm getting a lot of chat messages here that you are all experiencing lag. So by the time to clarify what you mean by that is that by the time I got on Zoom, you were still seeing me on YouTube.
Yes, that's correct.
And where was that? Where was I at on YouTube?
We can time it next time and let you know.
Yeah. Okay. That's okay. That's okay. I can wait an extra 10 seconds. Typically, it's, it should be no more than 20 seconds. That can feel a lot, right? Because we're moving at a quick pace, but I'll wait another 10 seconds because I can see myself on the stream as well. So I typically only wait until the activity shows up, the activity screen shows up on the YouTube, and then I'll turn on my Zoom. Okay. But that wasn't quite right, Marta. That you kind of closely describing the standard error. Okay, so the standard deviation is not for the linear fit or any fit for that matter. Let's see, Porter, do you want to take on the standard deviation question? Intuitively, what does this? Yeah.
It would just be like the average distance from the mean that a certain data point falls on.
Yeah, and it generally describes how far away the data is from the mean. And if you don't know anything about the data, you just have data, the mean is the simplest descriptor. A large standard deviation means the mean is really bad descriptor of those data. A small standard deviation generally means that the mean is, all the data are pretty clustered around the mean. Now, Marta's answer is for the third question, which is describe the standard error. The standard error is the equivalent of the standard deviation, but around the fit. It doesn't have to be a linear straight line. It's just any regression fit, and we will discuss this today. So the standard error applies to any kind of fit you will be using around the data. All right. Okay, I will see you on the other side. I'm going to mute and stop my video. All right, so as we just discussed, this was kind of quick reminder of the properties of data. But last time we derived the standard regression for a straight line, and we called that linear regression. So now we're going to continue and try to understand what we can do. Clearly, a straight line is not going to describe all sorts of data. You see data going up and down in cycles. Sometimes you see data behaving exponentially or all sorts of different combinations. So we want to see if we can use more complex models to fit those data. And we're going to start with a simple example, just an extension of the straight line. And instead of using a straight line, what if we want to use a quadratic? So a0 plus a1x plus a2x squared. And note that what I'm highlighting in red are the unknowns that we're looking for. Okay, the x values are going to be known data because we're going to take this model and apply it to the known data. So we have the x values really. The x's show up non-linearly, but the coefficients show up linearly. That's very important. And we will see why. That's why we call this, all of this, linear regression. So my question to you now is, do you think with this model, do you think we're going to get a system of linear equations, and why or why not? So take a moment to think about this, and I will see you on Zoom.
I can go.
Go ahead, James.
I think that it can be turned into a system of equations.
A system
Linear
of
equations.
linear equations. Why?
Because the a values aren't like inside of the x values, so they won't be affected non-linearly with the data points.
That's right. Yeah, so the coefficients show up in a linear fashion. In other words, the unknowns that we are after, they are just linear combinations. They're not inside nonlinear functions like sines and cosines, right? If you had cosine a0x, then you cannot separate that. We're going to talk a lot about this later, but for now, yes, this is the correct answer, okay? I'll see you on the other side. Okay, correct. As James said, what we are going to obtain here is a system of linear equations, and we're going to prove this to you. Now, note one thing, and I noticed this in your exam. A system of equations doesn't have to be linear. You can have a nonlinear system of equations, and we are going to discuss that in the next chapter. But when we say specifically a system of linear equations, then that's a system that you can write in matrix form, AX equal B, and then you can solve using the methods we learned about. So yes, we are gonna get, I know that we will get a system of linear equations, and gonna actually have you show it in a second. Now remember, the way we do the least squares regression, we choose to say, okay, we're gonna fit this model to the given data. So this is our model, f of x. We're gonna apply it to the data, so we get fi, and we're gonna, the difference between the original observed dependent variable, yi, minus the model applied at the independent variable fi, that is going to give us the distance between the observed data and the model. And then we're going to try to minimize this sum. That's kind of the aggregate error norm. So in this case, we have this form. You just substitute simply fi, and then you get this, and you apply this for each point I in the data set. And S is minimum if the derivative of S with respect to each of the unknowns, those are A0, A1, and A2, is identically equal to 0. Now I ask you derive the resulting equations and then write them in matrix form so that you can show to yourself that indeed we do get a system of linear equations. All right, I'll see you on Zoom. All right, so if you're still listening in, go ahead, just keep looking at the YouTube screen. You'll see the summation, the equation for the summation. I want you to differentiate that with respect to A0, A1, and A2. Take a moment, keep things in summation form, be easier for you. Just if you can at least get one of these equations, that'd be great. That's going to be an exercise that you're going to have to do over and over again. Okay. Because I want to show you how painful this is. And then I'm going to show you a technique that's really cool that you don't have to worry about any of this anymore. All right, do I have any answers? Anyone got something to share, or you still need some more time? Maybe pick one of those, like partial S with respect to A0, or with respect to A1 or A2. If you've got at least one of those equations, just let me know. Sami, do you want to say something? And then Abby, go ahead.
Sure.
Yeah.
So should I just say the first one?
Go ahead.
So the partial derivative with respect to A0 is the sum of -2xi squared times yi minus A0 xi squared minus A1 x1 minus A0.
Okay, that was a little bit
sorry.
difficult for me to see, but At least you tried. I'm trying to think about what you said, whether. So essentially, when you differentiate, I can see where the negative comes from because it's multiplying a naught. So you have that negative sign, multiply the 2 in the power. So nu prime times un minus 1. So in other words, what I expect to see is minus 2. So summation of minus 2 into yi minus a2 xi squared minus a1 xi minus a naught, right, in parentheses, right? And Abby, do you want to do the second one?
Yeah, so I get minus 2xi times
the whole
everything
thing.
that's
Exactly. And the third one is minus 2xi squared into this whole summation. That's perfect. Okay, I'll see you on YouTube. Okay, so just like we discussed on the other side of the internet, it's fairly straightforward now doing these derivatives. This is what you get. As expected, you're going to get 3 equations with 3 unknowns, and the unknowns are a0, a1, and a2, and they do show up linearly, thankfully. You do some manipulation, and you get this fancy system of linear equations, because remember, the unknowns are the a0, a1, and a2, and they show up linearly. Everything else, all of these crazy summations with the xi's and the yi's, they're all known quantities, right? Those were given to you from the observed data. Okay, and then you convert this into matrix form. You get 3 equations, 3 unknowns. Indeed, we just showed that you do get a system of linear equations, although your regression model was nonlinear. It looked nonlinear. It looked like it's a quadratic, right? But it is linear in the coefficients, and that's what matters here. Okay, now next we learned how to do this in by hand. So we programmed this entire matrix, and we did the solution A inverse times right-hand side, or np.linalgebra.solve. And the next way to do it is to learn how to do it with built-in Python functions. Okay. Now I want to go back to interpolation and remind you of the function Polyfit. The reason I like to use Polyfit to do regression with Python, clearly, if you haven't realized already, there are hundreds of ways to do the same thing in Python or any programming language for that matter, right? And I'm only showing you one way. You might choose to do it in a different way. I'm just trying to show you the simplest way, the easiest barrier, the method that has the lowest barrier of entry, so that you can apply this as you move on in your career and your studies. Now, remember Polyfit. Remember, we said for a polynomial of n plus 1 data points, you could fit a polynomial of order n, correct? And then we used Polyfit. We gave it the degree n. And then if you chose a different number for n, I told you that is going to give you a regression. And this is exactly what we get here. So this is how we're going to use Polyfit. You remember using Polyfit, you give it the independent input variables and dependent input variables and a degree for the polynomial, and then it does a fit. If n is less than the number of points, or if n is equal to 1, for example, you're going to get a straight line regression. If you have 1,000 points, n equal 1, you're going to get straight line regression. If n is equal 2, you're going to get a quadratic regression. Now, by extension, if n equal 3, you're going to get a cubic regression, right? So, and you're going to get a straight line as well. Now, once you get the coefficients from Polyfit, so Polyfit is going to do everything internally. It's going to build this coefficient matrix, and it's going to solve it, okay? And it's going to return the coefficients of the polynomial, the a0, a1, and a2, et cetera, et cetera. So those are stored in coefs over here. And then remember last time when we did the working class, the coding activity, we had to build also so we got the coefficients. Now you need to build the model, and we had to define a routine called, Y model, or my function, or my linear fit, and to apply a0 plus a1 times x. Well, with built-in Python, all you have to do is use polyval, for example. You use polyval, you give it the coefficients, and you give it the data where you want to apply this model, right? So Polyfit gives you the coefficients, the a0, a1, a2, etc. Polyval essentially takes those coefficients and gives you a0 plus a1x plus a2x squared, however many coefficients you have, and applies it at all the values xe. Okay, and if this gives you the best fit polynomial, like I discussed. So let's go ahead and do this in Python now. And last time we did this using our own programming to do the inversion and get the regression done. Now we're going to use the Polyfit. So open up your height versus femur data that we worked on last time. Last time we left off, I think, at the r² value. We did everything left off at the r². Now we're going to do the same thing using Polyfit and Polyval. Okay, I'll see you on the other side. All right, everyone. I am here on Zoom right now. Let me see. And I am gonna share my screen with you. This is desktop 2. I'm gonna share my screen. Okay, and I am gonna bring in the height versus femur data that we were working on last time. So now you can watch me on Zoom, although this is all going to be recorded on in YouTube. Okay, so you can follow through after we're done if you want. So this is the Jupyter notebook that we've had last time. Go ahead and open it on your end. I'm hoping you got that already. Okay, so go ahead and execute it. Execute what we've done. I had the example. We had some boilerplate stuff, the xi, yi array. We plotted the data. That was one of the questions in the exam was, what do you do when you're presented with data? And yeah, first thing you do is plot it. Some of you answered flirt with the data, and that made me laugh so much because that's the word I use. So thank you. I appreciate your attention. That really made me laugh. But yeah, first thing you do is just plot the data, right? Plot the data. Always plot it. Okay. So last time we did this matrix. We implemented this matrix by hand, and you can remember we had n and a. The putting in the array was cumbersome, etc., etc. And then we constructed the right-hand side. Go ahead and execute all of this. Then we solved the system of equations. We got the coefficients, a0 and a1. And then we had to define the model. Otherwise, how are you going to apply the regression model to do any prediction? You need a function or a routine to call so that you can make a prediction, right? So we defined this routine as y model. It takes any value and then takes a0 plus a1x, and then we did a prediction for a femur length of 40 centimeters, and we also plotted the regression line.
Screen your notebook so that we can see it a little better.
Excuse me. Yes. So Abby, you want me to zoom in a little bit like this? Is this better?
Yeah, it's better. Yes, thank you.
Okay. Thank you for letting me know. It's hard for me. Okay. Is this good for everyone? Okay. So you should be able to. I'm hoping you're executing this on your end as well. Shift enter, shift enter, shift enter, etc., etc., etc. Okay. We did all of this. R² value. Okay. Good. Now we're gonna use built-in Python Polyfit, okay, to do this. Regression to a straight line. Regression to a straight line using Polyfit. Okay, now be careful about my language here. This is all linear regression, but don't think that linear regression is only to a straight line. Linear regression can be to a quadratic, as we just showed in class. The word linear comes from the fact that the resulting system of equations that governs the regression is a linear system of equations. Okay, we're going to see next, we're going to be able to do linear regression on sinusoidal functions. Okay, as long as the resulting governing system of equations is linear. That's why we call it linear regression. So here what I'm doing, linear regression to a straight line, okay, specifically. All right, so what are we gonna do? We're just gonna define our coefficients equal numpy dot polyfit, oops, polyfit. Now, what did we say with polyfit? We wanna give it the xi and yi data. Couldn't be any easier. We already have xi and yi defined, okay? And if you go up here, these are the xi and yi arrays, okay? Now, the third argument in polyfit is going to be degree. That's the order of the polynomial that you want to fit. Now, if degree is equal, if you have n plus 1 points and you put n, you're going to get an interpolant, okay? But if you put any other value that is less than the number of points, then you're going to get a regression. So here I'm going to put 1, and I claim that this is going to return a straight line regression. And I'm going to print the coefficients here. And look at that. So we got 1.004329 and 123.207. So let's compare those two numbers to what we got when we did this by hand, or when we did this kind of the brute force approach. Where was that? That was right over here. You see, 123.207 and 1.004329. Python always returned this in the opposite order. That's fine. But I hope now that you can confirm that this is indeed doing a linear regression. One of the questions on the exam was, what do you do with, how would you verify your Thomas algorithm? You compare it to a built-in function. And that's how I would verify my regression makes sense. I'm going to compare it to the Python built-in function. Doesn't mean the Python is, you know, holy and doesn't have any mistakes, but in general, I bet you that it's pretty darn, if there was a mistake, someone would have caught it, okay? So it's more likely that I have a mistake than Python has a mistake, okay? So see how cool this is? This is pretty fast, pretty quick. Now I can use Polyfit to evaluate my regression, polyval, sorry, to evaluate my regression, do a prediction. I'm going to do np dot polyval. Now polyval takes the coefficients and takes a single value. In this case, let's take the 40 centimeter long femur. That is going to give you 163.38 centimeters for the height of the individual. Let me compare that to what we got over here. If I scroll up, see, my Y model gave me also 163.38. And you can do the same thing. You can plot the regression line, okay, the regressed line. I'm just going to copy this using the polyval. So plt.plot, I'm going to plot my regression line, which is np.polyval now, up with using the coefficients and applied at xi, okay? And when I plot this, I'm going to get the same exact thing, okay? So now I am going to ask you to repeat this, but let's fit in a quadratic. All you have to do is change one number using Polyfit. Go ahead.
Would you change your 1 to a 2?
Yes, Sarah, good job. Thank you. Just put a 2 here. Now that's going to return 3 coefficients, okay? And those are the coefficients of the polynomial, of the quadratic regression. Now I try to evaluate that. It's still around 163. Now notice one of the coefficients is quite small because really the data is not really quadratic. The data is more closer to a straight line than a quadratic. And then when I plot this, it's still almost a straight line, right? There's a little bulge over here in the middle. You can barely see it, okay? All right, so how can we do a cubic?
Same thing, but change the 2 to a 3.
Yes. All right. Great. This is what we got. We evaluate, we plot it. Look at that. It's a little bit, it's trying to capture some of the curvature in the data. Okay. Now it looks jagged like this because I only applied it to the XY values. If I wanted to do something more thorough, I would do X range. I would do mp.linspace from min xi to max xi with 100 points. Okay, and then I plot it on X range just to get a nicer curve. See what you get? So you're starting to capture some of the variation. If you want to do a quintic or whatever, right? You just change that number, okay? You should be able to do this now also manually, the brute force approach. The matrices are going to be complicated. Now there is a catch over here with using polyval. And that's why we need to learn how to do regression manually. Can someone think of a catch? What if, think about it for a moment. What if I want to play around with the form of that polynomial? Would polyval be able to, polyfit allow me to do that? So let's suppose that we want to fit the following. We want to fit, we want to use the model A naught plus A2 x squared plus A5 x to the 5. Oops. So suppose I wanted to use this model. Can I do this with Polyfit? No, I cannot do this with Polyfit because Polyfit is going to assume I have a standard full polynomial. For this model, I have to derive the equations by hand and then program the equations. Okay. Can someone?
Are you saying?
Yes.
Are you saying that the polyval assumes that you have like an x to the third, x to the fourth term
Correct.
as well?
It has the full polynomial form, a naught plus a1x plus a2x squared plus a3x cubed and so on. It doesn't, there's no way for it to even give you this kind of flexibility. It's because this flexibility makes the complexity explode in terms of how much complexity you have to deal with. So for cases like this, you have to do this by hand. So that's why we learned the other way. So you would have to go and apply this model, derive the summation, the least square summation, okay, and derive the equations, put in the matrix, solve the matrix, get the coefficients, and do a plot and do a prediction, okay? But next, I'm going to show you a cleaner and easier way to having to do an alternative to having to do this full derivation every time, okay?
Hey, could you show us your X range function again?
Yes. So it's simply a linspace. Yeah, so Carl, the reason I did this is because I wanted to see a smoother curve. So I wanted more points between the minimum and the maximum input independent variables. Okay?
Yeah, mine's showing an error because it wants only 10 instead of 100. I'm not sure why.
It says what? What does it say?
It says the dimensions don't match between the X and the Y values. The one is 100 and one is only 10.
Yeah, we can talk about this after the lecture, okay? All right. Are we ready to go on YouTube again? Okay. It's gonna get a little intense now. All right. I'll see you on the other side. Okay, now it's gonna get really exciting, and I'm really excited about this. I put these slides together yesterday night and today because the way I used to explain them in previous years just didn't make sense to me. But I think this year I'm gonna explain it in a much better and more intuitive way. And the title of the next section is general linear regression. Okay, focus on the word linear regression. Linear regression does not mean a straight line. We just did linear regression using a quadratic, a cubic, a quintic, whatever polynomial you want to do. You can use Polyfit or do it by hand. Okay. So let's suppose that you have the following data. Okay. So these blue dots, right? So they look like they fit a form of a sinusoidal function. Agree? Yeah, they're kind of cyclical. They're going, up and then they go down, right? So clearly, a straight line is not going to be a good representation of those data. I want something better. It looks like a good model for those data would be of the form of a combination of some coefficient multiplying a cosine plus another coefficient multiplying a sine, trying to balance sines and cosines, okay? Now, my question to you is, derive the equations governing the regression of this model on those data. And I'm claiming that you are going to get a system of linear equations, although the model is highly nonlinear. Sines and cosines are quite nonlinear, right? But I want you to do this by hand and come up with the system of equations that results from doing a least squares regression on this model. Now remember, you are minimizing this function, yi minus fi squared. Keep it in summation form, substitute f over here, and then see what happens, okay? I'll see you on the other side. Take your time. I want you to spend a couple of minutes. Just if you do one of the conditions, remember we're minimizing the sum of the squares with respect to what? To the coefficients a and b, okay? So you're doing partial s with respect to a and partial s with respect to b. Just do one of them. That'll be sufficient. Just want to show you how complex this can get. You should have some sort of answer right now. You're not differentiating sines or cosines. You're just differentiating with respect to a. All right, let's see. I'm gonna spin the wheel.
I think I've got it.
Carl, okay, let's wait. Let's see. Let's give Sydney a chance first. Hey, Sydney.
Hey, so just putting the fi,
well, ft into fi.
Mm-hmm.
So yeah, it would just be the sum of yi minus a cosine t minus b
A cosine
sine
ti minus b sine
Yeah.
ti, correct? Okay, so when you
Yes, so-
minimize that, you need to differentiate it with respect to a and with respect to b. Did you try to do one of those or not yet?
Yes, a.
With
That's where I
respect to
got.
a, okay.
So
Yeah.
that would be -2 cosine ti, well, the sum of, sorry.
Hmm.
And then yi minus basically f of t.
Sorry, so the partial with respect to a is -2 sum of cosine ti into yi minus f of i.
F of
fi.
t.
Yeah, f of
Fi,
ti or
sorry.
fi. That's right. So who wants to take the second one?
Sorry.
Carl, do you want to do the second one? Partial s with respect to b?
Yeah, sure. So it's basically the same thing,
Yeah.
just sum of -2 sine t and then the rest of it.
Sine ti, yep. Don't forget the ti. Those are the input data. So f of f sub I is the equivalent of f of ti. That's the model evaluated at the ith independent observation. That's correct. I'll show you the equations in a second, and we'll see why I'm presenting you and making all of this painful for you. Okay? All right, so I hope you had a chance to just do these derivatives. I'm sure with more time and practice, you'll be able to do them. But as Sydney and Carl did, they got the right answer. So you simply take this summation. Well, not simply. It's reasonably, you take the summation, you put instead of fi, you just apply the model. And see, I made a mistake here. This should be a cosine ti minus b sine ti. It's important because those are input data that you know, okay? And then s is minimum. If partial s with respect to a is 0, that gives you this -2, you get the cosine ti, etc. And then same thing over here, partial s with respect to b, you get -2 sine ti, etc. Then you do the same thing, you combine everything with each other, and then you get this nasty coefficient matrix, okay? Now, and then what's going on whatever is going on the right-hand side, okay? And we're still solving for A and B. Now, this is still linear regression. Why? Because it resulted in a system of linear equations, although the model was highly nonlinear. Okay, that's very important to recognize. Now, suppose you wanted to fit another kind of model. You had sinusoidal data with some exponential decay or something weird with it. Yeah, someone came up with this model, a cosine t plus b sine t plus c e to the minus t squared. This is still linear regression. It's a model that's highly nonlinear, but the way the coefficients are presented, they are presented in linear fashion. And this model results in this system of equations. Okay. Now, why am I showing you this? Clearly, having to go define the summation. And so there are two things to take from it. The first thing is that you can develop very complex models, whatever you want, really, as long as the coefficients show up linearly. Okay, that will still result in linear regression. Second, the coefficient matrix is really annoying to derive because you don't want, every time, you don't want to take this, define the summation, take the derivatives with respect to coefficients, and then build this matrix. What if you had 50 terms over here? It's going to get really annoying and cumbersome, okay? So that's the purpose of this discussion, is going to get you to a point where we're going to simplify all of this and derive this system of equations very simply. But first, I want to introduce the idea of the basis function. So remember, the first thing to learn from this is that you can develop very complex models that can be highly nonlinear. As long as the coefficients show up in a linear fashion, you're going to end up with linear regression. Now, these models, to make this more fit in mathematical framework, whatever the coefficient is multiplying, the function that the coefficient is multiplying, we're going to call this a basis function. It's just a fancy word that says the model we're using is going to use the following, is going to build a linear combination with these functions. We call these functions the basis functions. That's it. So in this case, the basis functions are cosine t, sine t, and e to the minus t squared. Okay, so I'm going to ask you now the following question. I want you to list the basis functions for these models. The first model is a plus bx. The second model is a naught plus a1x plus a2x cubed. Third model is a naught plus a1x plus a2 e to the minus x squared. And the third model, the last model, is log a x to the power b. Okay, I want you to take a moment now and think about what just list the basis functions. Okay, just list what they are. Like I listed them in the previous slide. The basis functions over here are cosine t, sine t, e to the minus t squared. Okay, I want you to do the same for these models, and I will see you on the other side. All right. Some of you are still probably catching up with YouTube. Go ahead and just list the basis functions. Tell me what they are for each of those models. Feel free to expand the last one, okay, because it might seem that it is nonlinear or just kind of weird, but expand it and see what happens, okay? And then give me the basis functions. All right, do we have any takers? Okay, spinning the wheel. Hayden, are you with us?
Is the first one just 1 plus x?
That was Sydney?
Yes.
Yeah. Yes, it is not 1 plus x.
Just
1 comma x, right? So
x,
we're
yeah.
listing the basis functions.
Sorry.
Okay, Hayden. Okay, so the second one. Let's see who's going to take the second one. Maxwell, are you with us today? Maxwell is not. Okay, Anna. Okay. Okay, I'll spin it one last time and then I'll pick from the Tess. Tess is usually with us. No Tess today. All right, so let me take some volunteers. Not the usual gang, someone else.
Would the second one just be 1 comma x and then x cubed?
Correct. Thank you, Jeremy. All right, third one.
I have 1x and then e to the minus x squared.
Correct. Okay, that's great. Thank you, Bailey. Okay, let's see. Who wants to take on the last one?
I got 1 comma ln x.
Good job, Kaya. Good job. That's great. So do you want to explain to us how you did that?
Well, you have ln of a times x to the power of b, and that separates to ln a plus b times ln of x.
And log a is just a constant, right? So you call that capital A and then b log x. So you get 1 and log x. Great job. Thank you. All right, I'll see you on the other side. All right. Okay, so like we just discussed, you guys all nailed it. Good job. So whoops, I'm switching scenes. It was a wrong thing. Okay, so basis function for the first model is 1, x. Those are the basis functions, right? Don't be fooled by the a. A is not a basis function. This is just a coefficient multiplying really x to the power 0. So the basis function is 1 over here. In this case, you got 1, x and x cubed. The third case, you got 1, x and e to the minus x squared. And the last one, just like Kaya did, log a x to the b, you split that, you get log a plus b log x, and then you get a plus b log x, really, because log a is just a constant, okay? So that's critical. Now we understand the basis functions. Now the next step is to figure out a way of how to construct these complex matrices. So think about the catch that I discussed with Polyval. Okay, Polyfit. Polyfit would not allow us to construct any oddly formed polynomial, and it definitely would not allow us to construct models, crazy models that you might come up with, like the models I just showed you. In those cases, you have to build the coefficient matrix, the system of equations for regression by hand, okay? Now, doing the summation, the least square, the derivatives, etc., that's one way of doing it, but there's another way, a much cleaner way, the derivation of which is really complicated, but what I'm gonna do it now, the way I'm gonna do it is I'm gonna do it kind of by inspection to show you that how we can get that form. Okay, so the first step in thinking about basis functions and generalizing this, I'm just going to take a model, call it y model f of x, and I'm going to use two basis functions. I'm going to call them phi of x, remember, okay, and psi. Those are my two basis functions, and they're multiplied by two coefficients. The reason I chose two basis functions is for simplicity. Next, we're going to generalize this to an arbitrary number of basis functions. Now, I claim that the system of equations, if you were to do the summation and take the derivatives with respect to a and b, etc., this is the system of equations that you're going to get. You have some pattern over here. You get some phi phi and some psi psi, and then some phi psi, some phi psi. Okay, so there is a pattern emerging. So this must be coming from some systematic thing, systematic derivation. And we're going to untangle that together, but by inspection. Okay. So what I'm going to do next is I'm going to start by looking at this vector over here. This has two summations in it, and I'm going to claim that this is the product of the following two matrices. The matrix, this matrix that contains in the first row, phi1, phi2, etc. to phi n, and in the second row, psi1, psi2, all the way to psi n. What is phi1 and psi1, phi2, and psi2? They are the model, okay, the model applied at the first observation or second observation or third observation and so on. But it's the basis, the first basis function and the second basis function is psi, the first basis function is phi. Now, this y vector is simply contains the observed dependent variable. Okay, now go ahead and mentally do the matrix multiplication over here. Okay, you get the first row times the entire column. So you get phi1 y1 plus phi2 y2 plus phi3 y3 and so on plus phi n yn. That should give you summation of phi I yi, right? So that's phi1 y1 plus phi2 y2, etc., right? Now the second entry over here is simply the second row multiplied by the entire column. It's going to be psi1 y1, psi2 y2, and so on and so forth. Okay, I'm doing this by inspection. Okay, now this matrix is a little bit more complicated, but because I know the derivation, I'm going to tell you that this matrix is nothing more than the product of these two matrices. Now notice, I had already used this matrix over here. It showed up over here as well, and it showed up over here as well in a transpose, okay, in a transpose fashion. Now think about this. The first row over here multiplied by the first column is going to give you this first term, right? So you get phi1 times phi1, phi2 times phi2, phi3 times phi3, phi n times phi n. That's what you get, sum phi I, okay? Now for this entry over here, that's the first row multiplied by the second column. That's phi1, psi1, phi2, psi2, etc., gives you that term, and so on and so forth. Okay, so you should be able to verify that this product of these two matrices, okay, gives you this system of equations, okay? Now, it's critical that this matrix, to recognize that this matrix is really special. Okay, now, if you think about this matrix, what does it show us? It shows us in the order it was presented. We have basis function 1, which is phi, basis function 2, which is psi. They show up here. The first column contains the first basis function, and the second column contains the second basis function. Now, what are the rows? They are simply the basis function applied at the first observation, so phi1, psi1, the basis function applied at the second observation, phi2, psi2, and so on, all the way to phi n and psi n. Okay. Now, this is cool because all you have to do now is know this matrix, only this matrix, to build this entire complex system. So what I'm going to do, I'm going to call this A, okay? And we're going to call that vector y. That vector is really easy to construct. Only A, you have to know first basis function, second basis function applied at all the different observations. Now, what is this matrix and that matrix? They're simply the transpose of A. So if you know A, you multiply it by its transpose, then you're going to get your system of equations, because ATA gives you this coefficient matrix, and ATY gives you the right-hand side. And what do you need to know to solve a system of equations? You just need to know the coefficient matrix and the right-hand side. And then once you solve this, you get your alphas. So all you need to know is this coefficient matrix A. And it's really easy because all you have to do is list the basis functions in the order they appear and apply them at the different observations. Really couldn't get any easier than that. Now look at the generalization. This applies to models with arbitrary basis functions. Okay, now there's gonna be more indices. We're gonna show more indices. Okay, so my first basis function is phi1. My second basis function is phi2. My mth basis function is phi m. Remember, if you have n data points, you don't need to have n basis functions. So let's say you have 100 data points. You don't need to have 100 basis functions. You could have 2 basis functions, like a straight line, right? You could have 3 basis functions, like a quadratic, or 2 basis functions, sine and cosine. So, or 200 basis functions. It's up to you. So the number of basis functions has nothing to do with the number of data points. As long as the basis functions show up in a linear fashion, like I'm showing here with the coefficients, the unknown coefficients, alpha 1, alpha 2, etc., then you are good to go. Now with this model, I claim that this is the A matrix. Okay, now be careful about the size of this matrix. Think of it this way: the columns correspond to which basis function you're looking at. The first column is the first basis function, so that is going to be phi1, okay, phi1. And the second column is the second basis function, that's phi2, okay? And the mth column is the mth basis function, phi m, okay? Now the rows correspond to the observations, and that's the second index, okay? So that gives you, phi11 gives you the first basis function applied at the first observation, second basis function at the first observation, mth basis function at the first observation. The second row corresponds to the basis functions applied at the second observation, and so on and so forth. And I'll show you a really cool way of doing this in Python by just doing just knowing the first row, okay? Just doing it, knowing what the basis functions are, okay? So really, this matrix is just simply a replication. If you take your model and just move the phi's, put them in their respective columns, and then populate the matrix, then you will get your desired governing system of equations. Now, this is very important because once you are dealing with non-traditional regression models where you don't know the coefficient matrices, you have to do this by hand. Rather than doing the S and the derivatives every time, all you have to do is just do this. And there's a big proof that shows that this is how it works for regression models, okay, for all linear regression models. The way you use it is as follows. given n data pairs of the form xi, yi, so x1, y1, x2, y2, and so on, and a linear regression model of the form, this guy with m basis functions, build the regression matrix A, just like we showed. The columns correspond to which basis function, first column basis function 1, second column basis function 2, and so on. And the rows correspond to the observation. First row is the basis functions applied at observation 1, and then applied the second row, applied observation 2, and so on and so forth. And then build the y vector, which is simply the observed dependent variable that is coming in as an input to you, and that's just simply the y vector. And then to solve the system, ATA equal alpha equal ATY. Alpha is simply contains the vector of the unknown coefficients, but your coefficient matrix for regression is going to be AT, A transpose A, and the right-hand side is going to be A transpose Y. Okay? Okay, that was intense. You're going to probably have to review those slides, but once you do this coefficient matrix, this regression matrix, it becomes second nature, okay? Now, the resulting system of equations that you get, whether you do the summation S and you do the derivatives, or you follow this approach, these are called the normal equations, okay? There's just a name. There's a big history in linear algebra for why they call them the normal equations. But when someone tells you, oh, what are the normal equations for your regression model? It's these equations, okay? It's these equations. All right, so now let's do a couple of activities so that you can rehearse and train how to use this. Consider now the straight line model, A plus BX, and I want you, we know what the governing system, what the normal equations are. We know what the normal equations are because we derived those in class by hand with the summation and the derivatives, etc. Now I want you to get to this system of equations using the methodology I just outlined. So essentially just finding that regression matrix A, okay? So take the basis functions, apply them, find A, and then multiply it by its transpose and show that this is what you get, okay? All right, I'm here on Zoom. Some of you are still looking at YouTube. I want you to get started on trying to use the methodology I just outlined to get to this system of equations. Remember, the columns correspond to the basis function. So first column is first basis function, second column is second basis function, and so on. And the rows correspond to the observations, okay? So, excuse me, list your basis functions and populate them in the matrix. Just find A. It's sufficient to know A. Once you know what A is, you do A transpose A, and you get the final coefficient matrix. I'm going to copy and paste this over here so that it's easier for you to see. Okay, so if you look at first basis function, then the second basis function, and the slides are still showing on YouTube. Okay, so all I need from you really is to show me what A is and do the A transpose times A if you can, to prove to yourself also that this is precise. This is the system that you get. It's consistent with what we derived by hand. Okay. Does anyone have any leads? just list the basis functions, just like we did early on with the examples, what they are, and then fill out the rows. So in this case, you have two basis functions, right? They are 1 and x. So you're going to have two columns. How many rows? As many observations as you have. Just do 1, 2, and then and rows, and just fill in the values, and that will just give you the A matrix. All right, any takers? Let's spin the wheel. Megan, do you want to have a shot at this? Let's see, Megan. Okay, Megan is not with us. Maxwell, we already picked Maxwell, is not with us. This is a really bad random random name picker. Hey, Sophie, do you want to take a shot at this?
Professor, I only know that the basis is going to be 1 and x, right? But I'm not able to figure out for how many terms we're supposed to make the matrix, you know, so I'm kind of
Doesn't matter.
confused.
Assume you have n observations. So, you know, give me the first row.
So it's 1x, x squared, right?
No, why do you have x squared?
So that keeps on so we keep on adding the term, right? So for the, no?
No. Remember, we are listing that A matrix in the first column. It contains the first basis function, and the second column contains the second basis function. You only have two basis functions. They are 1 and x. Now, rows, you go row by row. The first row is at the first observation. So who wants to give me the first row? I think we picked Ellie earlier. Let's see. Parker, we also picked Parker. Oh, Jenna. Jenna, are you? Yeah.
Yeah, I'm here. Wouldn't the first row just be 1x1?
Yes. And second row?
Second row would be 1x2, right?
Okay. And the nth row?
1xn.
Yes.
Okay.
Yes. Good job. Thank you, Jenna. All right. I'll see you on Zoom and explain this. All right. So Jenna told us what we have, the A matrix is really couldn't get any simpler. You got to try it a few times, and then it will just come fixated in your head. Think of it intuitively. First, identify your basis functions. In this case, they are 1 and x. Those are your basis functions. Write them down. Put 1, x. Now start filling up the matrix. First row is first observation. Well, the first basis function is always 1, so it's always going to be 1. The second basis function is x. Applied at the first observation is going to be x1. That's the first observation. Second row, again, for the first basis function, it's always 1. Second basis function, it's x. Applied at the second observation, that's x2. Continue all the way to 1xn. Once you have A, you're done. You're done. Now you do AT times A. You take the transpose of the matrix, okay, and you multiply it by itself, and then you get the final coefficient matrix. Look at it, do it yourself. 1, 1, 1, 1, 1, 1, 1 times 1, 1, 1, 1, 1, 1, 1 is going to be n. It's going to be 1 plus 1 plus 1 plus 1 plus 1 n times. Now for the second entry, sum xi, it's 1 times x1 plus 1 times x2 plus 1 times xn, etc., etc. So you get some xi. Same thing for this guy here. It's x1, x2, xn dotted with 1, 1, 1, 1, 1, 1. You get some xi. And then the final entry is x1 times x1 plus x2 times x2, and so on and so forth. You get this last guy. And finally, the right-hand side is pretty straightforward again. You get 1, 1, 1, 1, 1 times y1 through yn. That's essentially y1 plus y2 plus y3 plus y4 gives you some yi. And same thing for the second entry. It's the xi's, x1, x2, and so on, multiplied by the y vector. All you have to know is the A matrix, okay? All right, so now we're going to take it up a notch. We're going to look at a model that has 3 basis functions. You don't have to do this. We'll do it together right now on YouTube, but this would be an activity you want to try at home. Okay, so you have this model, A plus BX plus CX squared. You got 3 basis functions. What do you do with the A matrix? You just write down your basis functions, 1, x squared, and then start populating the matrix. First observation, second observation, third observation, nth observation. Once you have A, you're done. A transpose times A gives you the coefficient matrix, and A transpose times the Y vector gives you the right-hand side. Solve this system of equations, and you're done. All right, now let's look at a more complex model. Let's look at A log x plus B cosine x. I claim that this is what you get, this complex summation, all right? What is A in this case? Think of your basis functions, log x and cosine x. Write them down. Log x, cosine x, and start populating. First row is first observation. That's log first basis functions at first observation, second basis function at first observation. So you get log x1, cosine x1. Second observation, log x2, cosine x2. Pop, 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 pop. As many observations as you have. You get log xn, cosine xn. Once you have A transpose times A gives you this guy. Okay, do the multiplication. You get log x1 times log x1, log x2 times log x2. So you get this sum log xi, log xi. Same thing for the second entry in the matrix. You get log x times cosine x. Okay, and same thing here, same thing there, and then the rest is history. Okay, I'm going to show you a really cool way of doing this in Python, but we will do it next time. I want to finish off the class with a just cooling off period, and I will see you on the other side. Okay. All right, I am back on Zoom. Some of you are still on YouTube. Take your time as you head back over. So I know this might seem too much, but I want you to go home and practice this. Come up with whatever models you want to come up with, build the matrix using this methodology, and then do it using S and the derivatives. And you'll see you get the same answer. This is such an easy way to find the system of equations that you need to solve for non-traditional regression models. So in Excel, for example, it might provide you with a couple of models for regression, like logarithmic or exponential and whatnot. But what if you want something more fancy? What if you want something fancier than that? You have to do this by hand. And this is the way to do it. This generalizes regression, okay? It's all linear because the coefficients show up in a linear fashion. Okay, we're gonna have a chance to ask you about, I'll send you a survey to ask you about the muddy points of regression. That will happen next Thursday, things that you are struggling with. But what I wanna do with the cooling off thing is, I was thinking the other day, and I'm not sure if this is gonna sound very cheesy or not, but I was thinking the other day, like, it would be really cool if we, like, you know how in life, as you go through life, something happens to you one day and you're like, darn it, I wish I can remember this thing for the rest of my life. Like, so like a life hack or like a tip or like a piece of wisdom or something you've done that's made your life significantly easier and made you be more functional and, not just like a rule of thumb, right? And I thought, we can do this in class, like every lecture, one of you would prepare a life hack for us or like a piece of wisdom or a tip and just come and share it with us. I do this in my group, in our group meetings every week, but those tips tend to be like 15-minute long tips, like a whole lecture about, anyway. So, but I don't want it to be that way. I'll give you an example. I'll start today with one tip, and it happened during the pandemic. So in February last year, I grew up in a civil war, and I've been through, I kind of know my way around prepping, for disasters, but nothing. I never expected what it would take to prep for COVID. But early on, when COVID was kind of on the horizon, we had come back from travel, seeing family. And I told my wife, you know what, let's prep. So I went to Costco. There wasn't a line. Next 2 weeks later, there was a long line. But I went early, I spent like $1,000 shopping for things that we might need. We had a baby coming a couple of months later. So we bought like 50 boxes of, formula, and we had like 1,000 diapers and 5,000 wipes, etc., a bunch of things. And I have my older kid. He's just 3.5 now, and if you have kids, they're going to be hanging out with you, and we're still working. So I wanted treats and bribes, to help them survive all of this. And one of the things was ice cream. We love to eat ice cream at home, and so every online order I would do, or every pickup order I would do from Smith, because they had limited capacity, I would add ice cream. So first on, I bought like 10 cans. I buy the Neapolitan one, the strawberry, vanilla, and chocolate. It's a mix for pleases everyone, and a lot of cones. So literally, I have like probably 50 boxes of ice cream in my freezer. I think more than Nancy Pelosi had in the pandemic. And so, but we started using them, but we would consume like one box. Takes us 2 weeks for one box, but I always rest assured that I have a lot of ice cream downstairs. 2 months pass by, and I go down, I need a box of ice cream, and I open it. It's all like frozen and like impossible to pick up. And I'm sure you've had that happen to you with an old can of ice cream, right? Something you had left over in the freezer, you grab it, it's all like frozen up and it doesn't taste good. It's all kind of crystallized. I'm like, oh my gosh, I lost all of those ice cream. I had to throw them away because I didn't know how to store ice cream. So my tip to you is how to store ice cream. Get that can of ice cream, put it in a Ziploc, big quart Ziploc, seal it. You don't have to vacuum it even. Just seal it to keep the moisture in. Throw it in the freezer. 6 months old ice cream in the freezer, as soft and mellow as you would have bought it fresh. So this is my life hack of the day for you. Okay. Now I want to volunteer. If you like this, if this is cool, we can continue doing this. Okay. I know it might be cheesy, and I'm trying not to distract you from class. So that's why I'm leaving this for the last 5 minutes. But if you have a life hack that could help us, or you want to just share it, if it's funny, or piece of wisdom, anything, please do share. I think, or a story about what's been going on in your life. This is a platform to do it. If you think this is a cool thing to do, we will continue doing it. So I'm gonna just ask you right now, is this too cheesy? Let me see. That's a solid tip from Dylan. Yeah, thanks, Dylan. Yeah. This is gonna be a story you're gonna tell all your friends and family. Wait for my other tip about how to peel a banana. I will leave that tip for another day. So who would like to volunteer for Thursday's tip? Let's see.
I can do it, Professor. I've got something for Thursday.
All right, great. So Mitchell on Thursday. All right, looks like you guys like this. Let's keep on doing it. All right. Thank you for your attention. Yeah, I'll have I'll have office hours today. So if you want to stop by, we're still grading your exam, but you should have that hopefully by the end of the week. Okay?